So thanks everyone for coming back, and I hope that I can do something useful. The other lectures have been really great, so I'm going to try my best here. So I'm just there we go. So each one of us has our own perspective of things, and sometimes the angle at which I look at things can seem very awkward from your viewpoint. And so one of my goals here is to try to convince you that my viewpoint is not that awkward. Somebody's phone here is on camera. Is that yours? Oh, okay. That's yours. Okay, the camera is. Sorry. I apologize. So before I get into today's talk, another exercise. You can tell from yesterday that I feel that you need to see examples before you see the definitions. It's hard to tell someone what a rhinoceros is without them having seen rhinoceri. That's the plural. So in these diagrams, we have some underlying graph. In this case, the graph is a vertex set and a directed edge set. It's a directed graph. The vertex set, let's call those three vertices A, B, and C. And the edges are A to B and B to C. And the red or root nodes are A and C. Unfortunately, you can't see them with the other participants here. But A and C are the red nodes. And this is the opposite of what Neumeyer did, but I call those the roots. And let me see if I can. No, I still don't have access to that. Okay, so here's the scaffold. So suppose my set X is simply just 1, 2, 3, 4, and the vector space, the standard module is going to have standard basis vectors 1 hat, 2 hat, 3 hat, and 4 hat. And now I'm going to put edge weights. So the edge weights are going to be matrices. So I'm going to put matrices on the edges of my little diagram, M and N, these two matrices. And so this edge weight from A to B is M. We just put label M on this, and edge weight from B to C is N. We put an N here. And the definition is just this partition function that you saw in Akihiro's talk yesterday. But there's a little addition here that the root nodes, we add information for every possible value of the root node. So we add wherever A gets mapped, we hold on to that standard basis vector, sigma of A hat. So if A maps to 1, then there'll be a 1 hat, and if C maps to 2, then there'll be a 2 hat. And just a sample term. So in the sum, there's the function sigma that sends A to 1 and B and C both to 2. And that contributes 1 is the sigma of A, sigma B hat of M. A 2 right here is the sigma of, right here is the 2, 2 entry of N. And we only hold on to A hat, sigma of A hat, and sigma of C hat. So this is this number here, which I identify as the matrix with a single non-zero entry. Okay, so I'm going to just treat these second order tensors. So if you calculate this, you find out that this diagram is exactly the same as this diagram, where if I just define this where I had just 2 nodes and only 1 weight, M times N, you would get the same exact outcome. Likewise, if I have parallel edges, same 2 matrices M and N, and I define this quantity right here, now my graph has 2 parallel edges, then I have sigma A hat, those nodes are A and C only, sigma A hat and sigma C hat, then I have the entry-wise product. Okay, so series reduction is matrix product, parallel reduction is entry-wise product. Okay, so in this definition that we'll start using tomorrow. Yesterday, I gave you a whole bunch of examples of imprimitive Q-polynomial association schemes that weren't P-polynomial. And one thing you'd like to know is, are there examples out there? And so you now know there are examples. But all the examples I gave to you were imprimitive, and they had a small number of classes. We spent time on 4-class Q-bipartite Q-antipodal schemes, which were exactly the same as real mutually unbiased bases. And 3-class Q-antipodal schemes are exactly the same as linked systems of symmetric designs. I didn't go into any detail of Donald Higman's work on linked systems of strong irregular designs, which are 4-class and 5-class Q-antipodal schemes. But these all had a small number of classes, and they were all imprimitive. In the end of so I'm going to spend a lot of time tomorrow on Suzuki's two papers. So Hirashi Suzuki published two papers back to back in 1998, one on imprimitive Q-polynomial schemes and another one on multiple orderings of Q-polynomial association schemes. And at the end of the paper, Suzuki says the author does not know any primitive Q-polynomial schemes which are not P-polynomial. I think he did know, it just didn't occur to him. The smallest example is the block scheme of the WIT design three-class scheme on 66 vertices. You can take any completely regular code. If you have a completely regular additive code, such as the Golay code or Hamming code, if it's an additive code, then you have a distance regular coset graph, and there's a dual association scheme, which is Q-polynomial and often not P-polynomial. The dual of the Hamming scheme, you just do the character theoretic dual and you get another Hamming scheme. But for the codes, you get many Q-polynomial schemes that are not P-polynomial. So I thought I would list to you all the things I know, and in the written notes, I list to you all the listed for you all of the Q-polynomial schemes that I know. And I would love to hear additions and corrections to that list. I put them on slides in preparing for these talks. It turns out 20 slides would take up pretty much the entire hour, and I still wouldn't tell you very much about them. So let me just give you a little taste of what they are. So Banai and Ito conjectured that if you have a very large number of classes, then P-polynomial and Q-polynomial coincide. Every primitive P-polynomial scheme, every primitive distance regular graph of diameter, I think larger than 8, I forget what the cutoff was, but very large diameter, is going to be Q-polynomial. And every primitive Q-polynomial scheme with a large number of classes is going to come from a distance regular graph. Okay? So I'm not going to offer you examples of Q-polynomial schemes with large diameter because this would be a very different talk if I had such examples. Banai and Ito in their book, they presented an infinite family of Q-polynomial schemes that were not P-polynomial, very arbitrarily large D, and they were bipartite doubles. So they were imprimitive, bipartite doubles of Hermitian forms dual polar spaces. Eric Morehouse and Jason Williford in 2016, Jason Williford is a master of constructions. He knows a lot of mathematics. They found a new infinite family of imprimitive Q-polynomial schemes that are not P-polynomial with arbitrarily large class number. And those are doubles of symplectic forms, symplectic dual polar spaces using this Maslov index. It's a beautiful paper with some really nice machinery. In terms of primitive Q-polynomial schemes, Pentilla and Williford introduced in 2011, they found an infinite family of 4-class imprimitive schemes, and then they found inside those an infinite family of primitive schemes, which are Q-polynomial, they're not P-polynomial, and they're not duals of P-polynomial schemes. So there's an infinite family of primitive schemes, which I think is very important. In the written notes, I've mentioned all the examples I know, and I think I'll stop there, just to let you know we're not talking about the empty set. Okay, so my goal today is to compare the basic theorems, very, very basic things we know about distance regular graphs, and look at the dual theorem and see if we know that theorem for Q-polynomial schemes or cometric schemes. So in association scheme, we have a set X, and we partition X cross X into binary relations. We require that one of the relations be the identity relation, and by convention, we always make that R0. So its adjacency matrix is going to be the identity matrix. Each of the RIs for my talks is going to be a symmetric relation, at least for today and tomorrow. And the crucial definition is that there's the combinatorial residue of the presence of a large a highly transitive automorphism group. So imagine configuration with as many symmetries as possible, write down what combinatorics would come from that, and throw away the group assumption. Okay, so the group assumption is gone. We just assume that any two things that are K-related, A and B are K-related, they look like any other two things that are K-related. If you would count, you'd say, okay, how many things are I related to A and J related to B? That's the same for any two things that are K-related. And you do that for all I and J. So it looks like there's an automorphism that takes AB to any A prime, B prime in the same relation, but it could be that there's a trivial automorphism group, and yet all this combinatorial regularity is still present. So you should imagine this as the combinatorial residue, the presence of a group being as large as possible, subject to preserving these relations. Okay, so that's the definition of a symmetric association scheme. we very quickly go to the Bose-Mesner algebra. We replace each of the relations by its adjacency matrix. So we have a bunch of 0, 1 matrices. A sub I has entry row B, column C equal to 1 if BC is in the ith relation, and 0 otherwise. We had the convention that R0 is the identity relation, so A0 becomes the identity matrix. We had the convention that the RIs partition X cross X, so every ordered pair shows up in exactly one relation, so therefore the sum of their adjacency matrices is the all ones matrix, which I use capital J for the all ones matrix. Assumed for today and tomorrow that the relations were symmetric binary relations. If A is I related to B, then B is I related to A, which means that the matrices will be symmetric matrices. And that regularity condition, the fundamental definition of an association scheme that these PIJKs exist, tell us that this vector space spanned by the A's is closed under matrix multiplication, and the PIJKs are exactly the structure constants. So this is the linear algebra definition of an association scheme. So the vector space spanned by A0 up to A and B, AD is a Bose-Mesner algebra. Now, the reason that it's different from just an ordinary commutative matrix algebra is that the AIs are 0, 1 matrices, and no two AIs have a 1 in the same position. So therefore, the entry-wise product of A3 with A5 is the 0 matrix. So therefore, the algebra, this vector space, is also closed under this second multiplication of entry-wise multiplication. And this interplay between these two multiplications, which is kind of hard to axiomatize without this explicit representation, this interaction between these two multiplications is really interesting, and it's at the crux of the topic. So the standard module, the set of all complex valued functions on the vertex set X, the Bose-Mesner algebra acts naturally on that by matrix vector product. And since the AIs are symmetric matrices and they commute, they pairwise commute, we have an orthogonal decomposition into maximal common eigenspaces. If one of the AIs generates the association scheme, such as a distance regular graph, these are just the eigenspaces of that graph. But some association schemes, no one of the AIs generates the entire algebra. So you have to find the maximal common eigenspaces typically. So now let's consider the matrices that project orthogonally. Think about the spectral decomposition of each of the AIs. It's a linear combination of orthogonal projections onto its eigenspaces. Now, these projections onto the orthogonal onto the distinct eigenspaces, we're going to call them E0 up to ED, or the matrices, because of the PIJKs, JJ0 is the valency of the jth graph. That is, each of the graphs is regular. The all ones vector is a common eigenvector. And so the projection onto the all ones vector is always one of these E's. We always call it E0. So E0 is a scalar multiple of the all ones matrix. The projection onto the entire space is the identity matrix. So if you sum all the E's, you get the identity matrix. A's were symmetric. The E's are linear combinations of the A's, so the E's are symmetric matrices as well. But now here's the interesting thing, that matrix algebra is closed under entry-wise multiplication. So if I multiply EI times EJ entry-wise, there are these structure constants. That's a linear combination of the EKs. And these are called the Krein parameters. Qijk is the Krein parameter. So the eigenvalue of EI entry-wise EJ is Qijk divided by the number of vertices on the kth eigenspace. It's just the spectral decomposition of the entry-wise product. And the entry-wise product as a principal submatrix of the Kronecker product is positive semi-definite. So the Krein parameters always are non-negative, and the eigenvalues of this matrix live between 0 and 1. So we know that these are non-negative, and these Krein parameters are what's interesting to me. So the change of basis matrices, which you saw in Akihiro's talk between the A's and the E's, very interesting. In Akihiro's talk, the P matrix was equal to the Q matrix. So P matrix is equal to the Q matrix. Here, we don't always require that. So the A's are a linear combination of the E's. So the PJI is an eigenvalue of A on the jth eigenspace. So it's the eigenvalue of AI. So these are algebraic integers, totally real algebraic integers. And now you can also write E as a linear combination of the A's. Now E is a projection matrix, so it's actually a Gram matrix for the projections into the eigenspaces. So the entries of this gram matrix are these Qij divided by the number of vertices. P and Q are almost inverses of each other, but also in the exercise in the notes, you can prove that P and Q are almost transposes of one another. If you transpose Q and scale the rows and scale the columns, you scale the rows by 1 over the multiplicities, and you scale the columns by the valencies of the graphs, then you get P. So if you've seen character theory of finite groups, you know that there's this orthogonality relations between the character table. These two orthogonality relations in the character table, this is a generalization of that. So this duality shows up all over the place, and just a taste of what happens. You have structure constants for the vector space under matrix multiplication. AI times AJ is a linear combination of basis elements, 0, 1 matrices, and the Pijk are the structure constants. But it's also closed under entry-wise multiplication. So EI entry-wise EJ is a linear combination of EKs, and the structure constants there are Qijk divided by the number of vertices. AI entry-wise AJ is either 0 or AI if I is equal to J. And EI times EJ, these are projections onto orthogonal eigenspaces. So if I is not equal to J, the product is the 0 matrix. The A's, if you multiply, you take this expansion in the previous slide. So think about this right here and multiply both sides on the right by E sub L, then AI times E sub L, almost all of these things are 0, just one term shows up. And that's what we're seeing right here. AI times EJ is a scalar times EJ. AI entry-wise EJ is a scalar times AI. The A is sum to the all ones matrix, which is the identity for entry-wise multiplication. The E is sum to the identity matrix, which is the identity for matrix multiplication. The trivial A is the identity matrix, and the trivial E is a scalar multiple of the other identity matrix. Okay, so we think of these two things, and you saw sometimes, like in Akihiro's talk this morning, there is an explicit duality. There is an explicit function between the two, but here we just have this sort of duality of parameters that guides our intuition. Association scheme is P-polynomial, so I'm going to leave out the orthogonal polynomials. I apologize to those who love to see this in terms of polynomials, but an association scheme is metric or P-polynomial. If you can order the relations so that the distance, so each AI is a distance I graph of, is the distance I relation of some A1, okay, a distance regular graph. So that requires that Pijk is 0 if k is too large, or if any one of them is larger than the sum of the other two. And it's non-zero if one of them is exactly the sum of the other two and still inside the range 0 to D. So a metric or P-polynomial association scheme is one that has such an ordering, and it might have multiple P-polynomial orderings. The odd graph and the Johnson graph, the same Bose-Mesner algebra. Strong irregular graph, a primitive strong irregular graph, and its dual and its complement generate the same algebra. So there can be several P-polynomial orderings. Okay? And these are exactly the same as distance regular graphs if you fix the ordering. And so we often study these things in the language of distance regular graphs. But if you dualize those parameters, if you instead say, let's just replace P's by Q's, we take this ordering of the primitive idempotents, E0 up to ED, and we call that a Q-polynomial ordering if Qijk is 0 whenever one of the parameters is larger than the sum of the other two, and Qijk is non-zero if one of them is exactly the sum of the other two and still inside the range 0 to D. So we've just dualized, and this is due to Delsart. I mentioned this yesterday. Just dualize the P-polynomial property and see what happens. And the best association schemes have both properties: the Hamming scheme, the Johnson scheme, the Grossman scheme, the dual polar spaces, the bilinear form scheme. All these association schemes, all the strongly regular graphs have both properties. So these P and Q polynomial properties are interesting. But let me just say that I'm going to use the dual intersection array, or the Krein array. So gamma 1 is a distance, relation 1 is now the adjacency relation of a distance regular graph if it's P polynomial. And all the parameters are determined by this intersection array, B0, B1, and so on, and C1, C2 up to CD, where BI, if I take two vertices at distance I, BI counts how many neighbors of the second vertex are distance I plus 1 from the first vertex. I should go this way because you guys are viewing this way. And if I take vertices A and B at distance I, then the X and Y at distance I, then CI is the number of neighbors of Y that are exactly one step closer to to X. And all the parameters are determined by just these. So for example, the line graph of the Peterson graph is a distance regular graph. It's an antipodal threefold cover of the complete graph, collapses down to K5. And here's the L1 matrix, P1JK, and the BIs are just the upper, there's a tridiagonal matrix, and the BIs are the upper tridiagonal, or the upper diagonal, super diagonal, is that what it's called? Okay, the super diagonal, and the lower super diagonal is where the C's are. So we're just recording that matrix in this little data, okay? So that's the intersection matrix. For Q polynomial schemes, we define the Krein array. So now L1 star, the Q1JK matrix, is tridiagonal with proper ordering. And we write down B0 star, B1 star, BD minus 1 star, and C1 star up to CD star, where BJ star is Q1J, J plus 1, just the dual of the BJ, and CJ star is Q1, J minus 1, J. For example, yesterday we spent a lot of time on the 24 cell, which has this sort of 4 cubes inside it. You delete any one of the 3 groups of 8 vertices, you get a 4 cube. The 24 cell has this tridiagonal matrix of Q1JKs, and this is the Krein array. 4, 3, 8/3, 1, 1, 4/3, 3, 4. Almost reverses of each other. That's the Q polynomial property. And the bumping up from 4/3 to 8/3 tells us that we're going to 3 Q-antipodal classes. There's a P polynomial world and the Q polynomial world, and people have been studying both over the last 50 years, but I think there's been a little more effort on the P polynomial side than there has been on the Q polynomial side. Here's a theorem, and this is so old, I don't even know who to attribute it to. This probably was known to Biggs and to Banai and to people probably by 1970, that if any of the AIs other than AD is zero, then A1 is 0. We're really looking at triangles. So A1 equals 0 means that the distance regular graph has no triangles. And what you're saying is that if there's any I where A sub I is 0, right, where I go out from X to Y, and all the neighbors of Y are either closer to X or further from X, and not exactly the same distance as Y from X, then there must not be any triangles. So this global information to local information, I think the distance regular graph people are secret Lie theorists, because there's all this attempt to map global, local to global, and so on. Well, Garth Dickey proved the dual theorem. There's a little bit less information than we have in the distance regular graph case, but in his thesis in 1995 at Wisconsin, this is the only mathematician I know who won an Oscar, by the way. Right? Not for this, by the way. So if any of the AJ stars is 0, except AD is strange. The AD star, this is the almost dual bipartite case. Any of the AJ stars is 0, then A1 star is 0. And on Thursday, I'll prove this for you, but I'm not going to prove that today because I want to use scaffolds. I want to use those diagrams to prove this. Again, I don't know who to credit this to. I think Banai and Gardner both discovered this a long time ago, that if I have an association scheme that comes from a distance regular graph, let's forget about polygons. Other than polygons, there's only 2 possible distance regular graphs. There's only 2 possible P polynomial orderings, if any more than 1 at all, either 1 or 2. So the maximum number of P polynomial orderings you can have is 2. And in fact, if I have a distance regular graph and the distance I graph is also distance regular, then I is either 2, diameter minus 1, or exactly the diameter. Okay, those are the only possible other distance regular graphs. And the thing that got me excited was Suzuki's paper in 1998, which showed that any association scheme other than a polygon has at most 2 Q polynomial orderings. The Q polynomial generator, if one Q polynomial generator is E1, then, and there's a second one, it must be E2, ED minus 1, or ED. Now, Suzuki had a little gap in his original version of the theorem, and Jianmin Hua and Kaishun Wang ruled out that last possibility with D equal 5. So let me write down the theorem in a little more detail. It says if you have a cometric association scheme with 2 Q polynomial orderings, and you assume that 0, 1 up to D is one of those Q polynomial orderings, and then the other one is one of the following. Either E2 is a Q-polynomial generator, and the ordering goes evens, evens, evens out to the end until it gets stuck and it comes down, back down on the odds. Or it goes out to D and then goes to 1 and then to D minus 1 and then to 2 and so on. And you'll see on Thursday, no, tomorrow, you'll see why these are the only possibilities, okay? And another possibility is it goes to D minus 1 and it can't get to 1, it has to go to 2 next. And you'll be able to prove, I think actually that's an exercise in the notes. So you guys will be able to prove that. Okay, so multiple P-polynomial orderings, multiple Q-polynomial orderings. The balances of a distance regular graph are unimodal. This is the one spot where I was going to use K0 is equal to 1. Sorry, V0, I call them V's. V1 is the balancing of the graph, that's some number. And they either go like this or like this. Okay, so there's a unique peak. It might be at the end, it might be in the middle, but there's no jumps at all. So there's some point, L star, L and L star. So let's, in this case, here's my L. In this case, maybe it's flat for a little while. Here's L prime and L, I think. Did I do it right? So this is what it's saying, that the valencies, the number of vertices at distance I from this vertex, grows, and then it might stabilize for a little while, and then it could go down or it could just grow and not go down. There should be a corresponding theorem for the multiplicities, the dimensions of the eigenspaces of a Q-polynomial scheme. There should be a corresponding theorem. We haven't been able to prove it. Okay, so this is an open problem. This is a conjecture. Think of Banayinito, that the multiplicity should be unimodal, and we don't have a proof. For distance regular graphs, we have quick proof because the CIs are a non-decreasing sequence, and the BIs are a non-increasing sequence. So therefore, you get this by just looking at ratios of consecutive sizes. But we don't have that for Q-polynomial schemes. In fact, for the Johnson schemes, it seems that when the class number gets large, the CJ stars for the Johnson scheme are actually unimodal. They go up and then they go down again. Okay, so the CJ stars for the Johnson scheme are not monotone. So you don't have the monotonicity. So we really need another technique to do this. The only case that's been resolved is Bruce Sagan and John Kaufman showed that if the association scheme is dual thin, so I have a cometric association scheme where every irreducible Terwilliger module is dual thin, projects to dimension 0 or 1 on each eigenspace, then you can prove the unimodality condition. And that's it. So we don't have a way to do that. So that's another problem. I gave you like 5 problems to work on yesterday. Here's another problem. And I need to conjecture celebrated result of Chejung Bang, Dubicus, Jack Colin, and Vince Moulton. Is that right name? Oh, I should be careful. I don't remember the first names. Shows that for any valency bigger than 2, there are only finitely many distance regular graphs of valency k. It's a very, very difficult theorem. There's all sorts of tools that are needed to control the eigenvalues moving around inside that interval minus k to k. Jason Milliford and I looked at the dual statement for any given m greater than 2. There should be only finitely many Q-polynomial association schemes whose first idempotent in the Q-polynomial ordering has rank exactly m. And it turns out that Suzuki's theorem on Q-polynomial orderings, remember he said there can only be 2 Q-polynomial orderings, we'll see a proof of that tomorrow. That tells you that the Galois group is at most a quadratic extension of the rationals, because every element of the Galois group of the splitting field of the association scheme acts faithfully on the set of EIs. And so it has to map Q-polynomial orderings to Q-polynomial orderings. And then you have to do a bunch of spherical code, Seidel type tricks to bound the size of that spherical code in that first eigenspace. But I won't talk about that theorem unless there's a request to talk about the proof of that. What about the imprimitive case? So a polygon of composite length, the polygon of length 20 has disconnected graphs. In its distance 2 graph is disconnected, its distance 5 graph is disconnected, the distance 4 graph is disconnected. Polygons of composite lengths have all kinds of disconnected graphs inside the association scheme. An association scheme is imprimitive if one of the graphs other than the trivial graph is disconnected. So distance regular graph, it turns out other than polygons, a distance regular graph is either bipartite, like the n cube, or antipodal, like the n cube, or both, like the n cube. Right, but the incidence graphs of symmetric block designs, those are bipartite but not antipodal. And the line graph of the Peterson graph, which I had on an earlier slide, is antipodal but not bipartite. So it can be one or the other. H Suzuki in 1998 proved almost this theorem, but for D large, for D bigger than 6, you have that if you have a cometric association scheme, which is imprimitive, well, either it comes from a polygon, polygons are a problem for everything, or it's Q-bipartite, that is Qij is 0 if I plus j plus k is odd, sort of the dual of an odd polygon. It's Q-antipodal, so these are the degenerate eigenspaces. So the degenerate idempotents are E0, E2, E4, and here the degenerate idempotents are just E0 and ED, or it could be both. Now Suzuki left open some possibilities. So he and Diana Serzo ruled out the possibility of D equal 4, where just E3 is degenerate. And Hajime Tanaka and Rie Tanaka ruled out the case where D is equal to 6, and 0, 3, and 6 are the degenerate idempotents. So these imprimitive schemes, now we know, okay, we know that there can be at most 2 Q-polynomial orderings. Imprimitive is either Q-bipartite or Q-antipodal. And the primitive things should all be P-polynomial if the class number grows. So there's sort of a navigable space here, and this got me really excited, and we got excited about studying these things and composing a list of examples. In coding theory, when you go from a code to a dual code, you have a linear code. The dual code, the size of the dual code is the number of cosets of the code, and the size of the code becomes the number of cosets of the dual code. Whenever you look at abelian groups, you have this duality where sub-objects correspond to quotient objects in the dual, and the quotient object corresponds to the sub-object in the dual. So we have to switch between, in primitive world, distance regular graph, like for example, let me use the board again, the line graph of the Peterson graph, we have 5 antipodal fibers. Now the dual object, we would look for a Q-polynomial scheme with 3 antipodal fibers of size 5, 3 Q-antipodal fibers of size 5. Okay, so the size of an antipodal fiber should correspond, any statement about the size of an antipodal fiber should correspond in the dual to a statement about the number of antipodal fibers, Q-antipodal fibers. So in a distance regular graph of valency V1, any antipodal fiber, the size of these fibers is at most the valency. Okay, it's at most the valency. We can't prove the dual theorem. This is still unresolved. In a Q-antipodal cometric association scheme, the number of Q-antipodal fibers is at most M1, but we can only prove that when the class number is odd. When the class number is even, the best bound we have is M2, the dimension of the second eigenspace rather than the first. And this really should be resolved. We cannot resolve this, and the tricks that you use just for distance regular graphs, the tricks that you use just aren't available to us. And so this is a big gap. This really should be M1. And in fact, if you look at the linked systems of symmetric designs that we talked about yesterday and real mutually unbiased bases we talked about yesterday, those you can prove that the number of Q-antipodal fibers is at most about half. This M1 should not only be an upper bound, but it should be very rare. Distance regular graphs with antipodal fibers of size V1, I think the only example I know comes from projected planes. Antipodal covers come from projected planes. No, antipodal covers are complete bipartite graphs. But it should be very rare to get anywhere close to that upper bound. And here I can't even prove the right upper bound. So this is unresolved. Godsell and Hensel studied antipodal covers of complete graphs, but they studied in general antipodal distance regular graphs. It's an very easy theorem that any subset of an antipodal fiber is a completely regular code in a distance regular graph. So any subset of an antipodal fiber, that's always a completely regular code. But if your antipodal fibers had size 4 and you had a group of automorphisms that had these sub-objects as orbits, then you can collapse those down and you can get an intermediate antipodal cover. And so Godsell and Hensel constructed these new antipodal covers by partially squashing previously known antipodal covers. So now you say, what should the dual theorem be? So, well, it's the dual of a completely regular code is a Q-polynomial subscheme, but completely regular codes don't always imply quotients. You have to have a partition in the completely regular codes. Okay, so if you think about what the dual object should be, you should say, well, it should be possible to take, instead of a subset of a fiber, you take a subset of the fibers and delete that, and you should still get a Q-antipodal association scheme. And we proved that with Misha Muslachuk and Jason Williford. We proved that any one of these subgraphs, you just delete a bunch of vertices from all the graphs in your association scheme, and you still get a Q-polynomial association scheme. The examples, that's kind of obvious. That's why I started yesterday with real mutually unbiased bases. If I have 7 real MUBs and I throw one away, I still have 6 MUBs, right? If I take a linked system with symmetric designs and I throw one fiber away, I still have a linked system with symmetric designs. So you can dismantle them. You can just throw them away one fiber at a time. And sometimes the fundamental thing to look at is just 2 fibers, 2 Q-antipodal fibers, which in the P-polynomial case, Q-antipodal becomes P-bipartite. Those 2 fibers are the 2 color classes of the bipartite graph. So sometimes you just want to go down to 2 fibers to study things. And so here, you can always delete Q-antipodal fibers and still get a Q-polynomial association scheme. So I view that as the dual of this, this result of Godsell and Hensel. Here's something that I think is really interesting. Sometimes you can take a distance regular graph and you can merge 2 of the relations. So for example, you can take the distance 1 union distance 2, and sometimes that's a distance regular graph, or distance 1 union distance 4 might be a strongly regular graph. We don't know really what's going on in the Q polynomial world, in the cometric world. So in the distance regular graph, so it turned out that you can build the Hemmeter graphs, and I think Ustimenko graphs also can be obtained by merging distance 1 and 2 in some of the classical P and Q polynomial association schemes. So what happens when you merge E1 and E2? Take the sum of E1 and E2 in a Q polynomial ordering. When does that generate a Q polynomial subalgebra? And I think I learned this from Akihiro Munemasa, but sometimes you internalize things and then they come back out and you think they're new. With Muslachuk and Williford, we showed that this is related to an extended Q-bipartite double, and you can build a double of this merge scheme. So this is sort of the dual of this Hemmeter thing, and we don't know that many examples. Really would be nice to have some more examples of this. In a graph and Seucher graph, I think you can do this. Products. When is the product of 2 distance regular graphs a distance regular graph? Now, there are all sorts of products out there. Let's take the first product that a student learns in graph theory, right, where you build a Cartesian product with vertex sets and you join 2 elements if they're equal in one coordinate and adjacent in the other, right? Sort of standard product. So the product of some number of distance regular graphs is distance regular if and only if there's some integer s such that the valency minus bi is s times I and ci is equal to I. Okay, so Bellarcorn and Neumeier attribute this to Michael Doob, Weichel, and Samuel Song. I don't know Weichel's first name. Who's your advisor? Paul Weichel. And I think that they saw various versions of this, and Michael Doob constructed the Doob graphs by throwing in this little impurity into Hamming graphs with Q equal 4. You can substitute for any 2 K4 cross K4 components. You can throw in a Shrikhanda graph, and the association scheme doesn't know the difference, okay? Or at least that algebraically it doesn't. What conditions can I take 2 cometric association schemes? Take the product association scheme, just take all Kronecker products of pairwise idempotents. That always gives you an association scheme, always gives you a Bose-Mesner algebra. Under what conditions is E0 Kronecker E1 prime plus E1 Kronecker E0 prime generator of a Q polynomial subscheme? This just occurred to me as I was writing up the notes, and someone could solve this by the end of this week. This is probably very low-hanging fruit. So that's where I stopped for today. And I will talk about the Suzuki theorems tomorrow, but I welcome your comments and questions.
Have any questions for Bill? Yeah, full please. Where's the microphone?
Yeah, about the unimodality of the MIs under the Q polynomial assumption. If you assume P polynomial in addition,
Then you have that.
then we do have the unimodality.
That's a good point. I should have added that. Sorry.
Yeah, and that's to Arlene Pascasio.
Okay, so you have unimodality when you're P and Q. Yeah, I should have been. I should have included that one. Thanks.
Yeah.
Hi, Crystal.
Hi, Bill. So if you look at 0, 1 vectors in the first T non-trivial eigenspaces of a Q polynomial scheme, those are T designs, generalization of T designs. It would be T designs in the Hamming scheme.
0, 1 vectors in the first
T non-trivial eigenspaces.
But not including the 0th eigenspace.
Yeah, I agreed these were T designs in the Hamming scheme.
No, I don't agree.
Okay.
Yeah. So
What were they then?
they're orthogonal. That's a 0, 1 vector orthogonal to all the other eigenspaces.
Oh, okay. I want the
But
most
if you want a 0, 1 vector that's in V0 plus VT plus 1 plus VT plus 2 up to VD, that's a T design.
Okay, so they're orthogonal to the non-trivial
They're
eigenspaces.
orthogonal to all the other eigenspaces.
First T.
Yeah.
Okay, right. So for those which have a second Q polynomial ordering, now you could again consider 0, 1 vectors orthogonal to the first T, and there would be this swap. Is it understood what those are?
I mean, the Johnson and Odd graph are the obvious examples to guide us, and I would still call them T designs in the Johnson graph. And I mean, there's a second Q polynomial ordering.
Yeah. So the Johnson doesn't have one, but the Hamming scheme has one.
The binary Hamming scheme, yeah.
Yeah.
So, I mean, they're not going to be designs of the same strength. So the definition of a T design in a Q polynomial association scheme, if you fix a Q polynomial ordering, a T design is a 0, 1 vector that's orthogonal to eigenspaces V1, V2 up to VT. Okay. And Crystal is asking if there's a second Q polynomial ordering, how do I interpret such a T design in terms of that Q polynomial ordering? And my answer is I don't know.
Working with Kai-Uwe Schmidt, and he asked this question to me, and we worked it out for the Hamming scheme that had the second one, and nothing exciting happened. It was just the same, but with some sign change, because the eigenspaces that are swapped in the second Q polynomial ordering are boring.
Yeah. So maybe, in that case,
So we just wondered if it was the same for all possible ones before we took the effort of computing another one.
But in that case, the characters, right? You take that last eigenspace and you take that character and multiply the third eigenspace by that character, you get the D minus third.
That's right.
And so
That's why it was boring.
So the T design, you might be able to interpret it combinatorially in terms of some kind of sign design.
Yeah.
But that is a very special second Q polynomial ordering. That's a very special case.
But isn't it always going to be like that? Because it's always like swapping.
Yeah,
The
but
second order can only be one of those orders that you listed.
Right, but you don't have such a bijection using that character, right? You don't have that you don't have a nice
You would for any bipartite scheme, yeah?
Q-bipartite.
For any bipartite scheme, all that would happen is that second thing would be swapped with the one with the same eigenvalue but negative.
Oh, you mean if it's P polynomial? What do you mean by bipartite? What's bipartite?
Oh, okay.
Okay, interesting. We could talk about it later.
Okay, yeah. Okay.
Paul's got more questions. Yeah.
Back to the
Also really good.
unimodality idea for in the Q polynomial case. So you have a dual adjacency matrix, A star, my star, that is according to the Q polynomial property, it's acting in this sort of
Tridiagonal fashion.
Tridiagonal fashion on the eigenspaces.
Yeah.
Sending the ith eigenspace into the some of the I minus first, I plus first.
Yeah.
Okay, so motivated by that, we take A star and break it up into a sum of 3 maps. the
Raising.
raising part, the flat part, and the lowering part.
Yeah, as I was listening to Sarah's lectures last week, I started doing exactly this breakup to attack this problem. Yes,
Okay,
very natural,
so
yeah.
Let's focus on the raising part.
uh-huh, Yeah.
It seems to me that what is needed in order to go to Unimodality
mhm.
is that the raising part,
Talking about this matrix.
yeah, okay, call that R.
Mhm, that's the raising operator, yeah.
So if we start it in some eigenspace EJD, where J is less than halfway, J is less than D over 2.
Mhm, mhm,
Okay, now we apply our multiple times. We apply our D minus 2J times
mhm.
to take us from VJ over to D minus J. Right.
Mhm.
So if you can argue that that is
Injective. That's Dennis Stanton had this stronger version of unimodality. Dennis Stanton conjectured also that M sub j is less than or equal to M, the dimension of this eigenspace is less than or equal to the dimension of that one. Continue.
yeah.
I'll just be your note taker. Go ahead.
That's the point. So
Mhm.
Arlene Pascasio and Henry results, assuming P-polynomial,
Mhm.
prove exactly that.
Okay, this is what she proved. Yeah.
Yeah, and so if that map is injective, then all the factors, the individual R's, as you go from J to D minus J, they must all be injective. So
Mhm.
and so the upshot is that MJ would have to be less than or equal to MJ plus 1 up to D over 2, as long as J is less than D over 2.
Yeah.
And so that gives you the weak increasing nature of the MJs up to halfway.
Uh-huh.
Yeah, so anyway, so the upshot, so it seems to me it all boils down to, arguing that this R is injective, for the first half of the sequence.
I think that this is probably doable. I was putting a lot of hours into this last week because I thought the right people are in this room to solve this problem. I bet you they'll have a proof by the end of the week.
Okay, so let's thank Biogen.
What I was noticing, you take any W in V1, and you can take, so let's call this R sub W, some diagonal matrix. And now you could take any vector, not just a column of E1, but you could take any vector in E1, and every one of these gives you a raising matrix, and then you can you can vary this continuously over W, right? You can say if it misbehaves at some point, I can move W and find out if it continues to misbehave as I vary W continuously across this eigenspace. So there are a lot more choices other than just the base vertex.